Okay, so yeah, these 5 minutes.
Ready? Ready? Yeah. Okay, so then let's start the presentation, please.
Ladies and gentlemen, my name is Thomas. I'm representing Austria. We're presenting the problem of 7
Can you try to speak as loud as possible?
Yeah. So the problem set statement was the following. To land a coin on the side is often associated with the idea of a rare assurance. What should be the physical and geometrical characteristics of a cylindrical dice so that it has the same probability to land on its side and one of its faces? So here you can see a demonstration of the problem. Here a cylindrical dice lands on the face. comparison or provide an error analysis defining the complementary conclusion. Now to the relevance of different parameters. So the first and most relevant parameter is the ratio thickness diameter. Not the absolute thickness and not the absolute diameter, just ratio. Now the second most important is coefficient of restitution, which I'll also refer to as the bounciness or COR in this presentation. Now another relevant parameter is the friction during impact, which is accounted for in the simulation but isn't varied. So we counted the friction, but it's not a parameter we varied. Now air friction may also play a role, but we neglected it. And now to the irrelevant parameters, the absolute scale, as I said, only ratio is important, and the mass is also not important. Now to the impact of the Rowing technique. The Rowing technique could be described as a set of three parameters: initial velocity, initial angular velocity, and initial height. And because of gyroscopic stabilizing effects, it has an impact on the outcome, because maybe, for example, if I spin the dice like this and let it fall, it is a much higher probability to land on its side than one of its faces. But we didn't vary the throwing technique because it would be quite difficult to quantitatively describe the throwing technique. Now to the first theory. First we made a 3D static theory, which means that we assumed that the coefficient of restitution is 0, so the coin sticks immediately to the ground, which means that the coin always lands on the side. So when we imagine a center, so the center mass of the coin, and draw a line to the ground, it always lands on the side that goes through this line. And by describing the cylinder into a sphere, we can say that the area of these sides must be equal, and we get to this formula. Or we don't necessarily have to say they're equal, we can just get this formula, and now get this graph for the probability of the dice. So here you see ratio thickness by diameter on the x-axis, y-axis is the probability of landing on the side, and as you can see, the longer the dice is, the more probable it is that it lands on its side. And for this, it would be a perfect ratio to come out to be 1 to 2 times the square root of 2. Now, then we approved the static theory because it isn't really good, because obviously the coin bounces, so a static theory isn't 100% true. And for the 2D simulation theory, we modeled the normal force as a force that suddenly increases with the distance to the ground, so like this, and the function you can see here. And the normal force and the gravitational force act on each point of the dice, because we described it as 4 points. And if the sum points upwards of all forces, it gets multiplied by the coefficient of restitution squared in order to implement also the coefficient of restitution. And here you can see which parameters we used for this formula together with the normal force, lambda, and the maximum force. And what's interesting, the absolute value of the maximum force isn't relevant. So we could make it 100,000 or 20,000. It should stay the same if it's numerically stable, because if the force is greater, it stays less time in the ground. But if it's higher, if the force is greater, it stays less time in the ground. If it's smaller, it stays more time in the ground. And all in all, it's the same. Now to the friction, we implemented dynamic friction and static friction with this formula. And the static friction is calculated so that the point that touches the ground shouldn't accelerate if static friction should act on this point. And whether it should act on these points, so we haven't a real nice mathematical explanation, but I put out a Python script. So if the normal force on this point is greater than 0.01, and the absolute value of the velocity of this specific point in the x direction is smaller than 0.001, and the static friction is smaller than the gliding friction, then static friction should be applied, and otherwise gliding friction should be applied. So that's how our 2D simulation worked. Here you can see the 2D simulation in action. So we implemented the Euler method in Python, and then these basic principles like acceleration x, acceleration y, and angular acceleration, we could calculate all the parameters, and we updated the position and velocity accordingly. And here you can see how the simulation really works. Like we have these 4 edge points, and on each edge point there are the set of different forces, and torques and everything is calculated for each edge point. So we can simulate this. And then we improved it by also making a 3D simulation using the Unity physics engine. Unity is an excellent rigid point physics system. And the simulation works by simulating 2,000 dice tosses at once, and it counts for every dice on which side it landed on. And we defined toss as a random height between 0.3 and 0.7 meters, a random orientation, a random angular velocity between -25 and 25 radians per second. So this is Unity, a great physics engine. And here you can see how the physics engine works in action. So here a singular throw. As you can see, it looks quite realistic. And here how the simulation works, 2,000 dice tosses at once. And it's important to know that the dice didn't influence each other, so were programmed that they wouldn't repel each other and influence the outcome of the probability. Now to the outcomes of the simulation, the orange line 2D theory, blue line 3D theory. The lines are just arbitrary fits to the points, as you can see here, the summation points. It's just a polynomial of, I think, 10th degree, just to visualize how the function would look like, but it's not that the theory really produced this outcome. You can see it's simulated for a coefficient of 0.61, because that's the coefficient of restitution the floor where I conducted the experiment on at. And for the perfect ratio 2D, be this number, and 3D this number. Now to the influence of the coefficient of restitution. Unfortunately, the 2D theory wasn't numerically stable for very small coefficient of restitution, because it sometimes stuck into the ground, and it was we had problems figuring out the real coefficient of restitution for the real probability for low coefficients of restitution. But nevertheless, we can conclude that the coefficient of restitution has a significant impact. And we can also conclude that the higher the coefficient of restitution, generally, both in 2D and 3D, the lower the probability of landing inside. Now to the experiment. I had 3 sets of each wood dices with varying thickness, as you can see on the right, and selected dices were tossed 200 times, 300 times, or 500 times, depending on the experiment. And I also programmed a Python app for my phone, so because I threw the dice and landed on the side, it would be very painful to note it on a piece of paper and then count the amount of points. So I programmed an app so I could just click it, which was easier for me to conduct the experiment. Now the statistical analysis, because if I toss the dice 200 times, so 1,000 times, and landed 200 times on the side, we could conclude that the probability is 20%, but it isn't necessarily true. It could also be 10%, but we had good or bad luck, but how you look at it, it could just differ. And to really calculate what the probability that it differs is, we had to use these confidence intervals. And here in this plot you can see the error bars, so the confidence intervals for a probability of 33%. And it is calculated using this formula. And so what really says the probability that my experiments lies between. So if I toss the dice n times, then the probability that the real probability of the dice lies between the upper and lower bound of the error bar is 95%. So the probability that the probability is some kind is 95%. And the 95% is just arbitrary that I can draw some error bars, because if I want it to be 100%, I have to draw the error bars from 100% to 0%. I have to make some, and I chose 95%. Now to the experiments for the coefficient of restitution. I measured the coefficient of restitution with each wood balls. I let them drop to the ground. And using this formula, I can calculate the coefficient of restitution. And it's important to note that the coefficient of restitution is equal for different masses. So it's not mass dependent. It's just a property of the material. And using this formula, and I filmed it with high-FPS camera, and using this formula, I can calculate the coefficient of restitution. Now to the experimental results. Here you can see a graph for ratio thickness by diameter, and here on the y-axis the probability that the dice lands on the side with the error bar. So again, probability that this point lies in this error bar is 95%, but I can't be sure. And now here the same experiment, but it's important to know this is for a 3 centimeter dice, so a dice with a 3 centimeter diameter. And here's the same graph, but also included with 2 centimeters and 4 centimeters. And as you can see, as I said before, the ratio really does doesn't play an important. Only the ratio is important, and the absolute scale and the mass aren't important. Now to the comparison, here you can see all my simulations, 2D simulation, 3D simulation, 3D static theory, and experiments in one graph. As you can see, the 3D especially is quite accurate, which we're glad to see. And yeah, this is the comparison. Now the error analysis, so the static theory has some deviations because it has dynamic and static. The 2D simulation has a too low probability for the side because there are no jurisdictional effects I mentioned before in 2 dimensions. 3D simulation has generally a great agreement. There are some small deviations, and there are material properties that further influence the outcome, like not only coefficient restitution friction, which we didn't account for, but it's also really hard to quantitatively describe, like properties of the ground. But now some conclusions, so theory, static theory, 2D simulation, 3D simulation. So the experiment spent more than 15 hours tossing dice and experimental coefficient restitution. And generally I did great agreement, and the deviations I analyzed. And yeah, thank you for your attention.
Thank you. Questions from your opponent, please.
Okay, thank you very much for the great presentation. My first question would be that you have said that, of course, the coefficient of restitution is, for example, mass invariant. Do you think that for dice of the same ratio but much larger, would there be the same coefficient of restitution present?
I believe that, so the coefficient of restitution is only constant or independent of mass in a certain range.
Yes.
In a
So
certain range.
a
And I believe-
certain
yeah, for the range I used, it was constant, but for much bigger dice, it may
Thank you
change.
very much. My next question would be, did you vary the surface at which you throw the coins?
No, as I said, I didn't vary coefficient of restitution.
Only one surface. Thank you very much. My next question would be, so you have, did you measure out the friction for that given surface? Because you need to
I
take
didn't
the
measure it since my floor, it was the floor in our basement, so I couldn't like tilt.
So you didn't measure any friction?
I did look up in the internet and literature.
Okay, so
and I
thank you.
used in my simulations, I used this value that
Okay, so they were fitted, right?
like fitted. No, I just looked up. I
Okay.
looked up from the literature.
Okay, thank you very much. Did you vary the moments of inertia of the coins? So the exact mass distribution, or did you only consider solid coins?
No, I didn't vary the mass distribution because I don't think. I mean, it would be.
Okay,
It would be interesting, but I don't think that
no
this
problem.
is.
My next question would be: did you analyze how does the inner workings of Unity work? So the inner workings of Unity's collision response. Did you analyze it in any way?
What?
The exact collision response functions of Unity. Did you analyze it in
No,
any way?
I didn't
No.
analyze
Okay,
it.
thank you very much. My next question would be: so you think the exact deviation between the 2D and the 3D theory are due to gyroscopic effects, right?
I believe that.
Okay, and in a random instance, what do you think? Is there an equal number of probability of the coin landing at a given impact angle? So yes.
Let's leave it for the discussion.
Okay,
Because it's not a trivial yes/no question, so I think you'll have time to discuss it.
Thank you very much.
Thank you very much. And time for preparation.
Okay, thank you very much for the presentation. I think we will have a great discussion. So I have my opposition about this three-sided test. So we all know the problem statement, the reporter has explained it quite thoroughly. So about the theory, we did not really like the theory because the mainly used theory was based on Unity, which was a physics engine, which brings up the question of own contribution into the problem. The experiments were quite plus because there were high quality measurements, some parameters were changed. Which parameters were changed really thoroughly. However, we have really missed changing, for example, of the surface. There was comparison with the measurement, but we will get back to our problem with fitting. Our overall impression is what was said was clear, and there were clear graphs and good animations. But we will get back to some low points. So the phenomenon was well explained. The phenomenon was sometimes reproduced, but I have really missed the changing of the surface, which is part of the phenomenon as well. The dependence on geometrical characteristics was thoroughly investigated for a given surface. However, I think that the physical parameters change is a really big part of the problem and should have been analyzed, and not only the coefficient of restitution, but also the two kinds of friction and so on. And quantitative theory, there was basically a quantitative theory. The exact quantitative theory was two-dimensional, which was then didn't use. And the really compared theory was based on Unity and wasn't fairly analyzed. So, about the overall evaluation of the solution, the strengths were the simple equations, the well-visualized simulations, the many measurements are extremely great. There was an extremely wide number of height ratios, so thickness ratio studied. There was a working setup with great shortcuts, a good error analysis, which was based on statistical methods. The experiments were really reproducible, and there was a comparison, and when there was a comparison given, there was good agreement. So we really felt like there were some possible ways to improve. There are some parameters which should have been included. I think that the dynamic friction and the static friction aren't irrelevant to the problem, as the reporter has stated. We will get back to the exact possible effects in the discussion. These could be all analyzed by varying the surfaces at which it was landed on, and also we really feel like that a static friction measurement is not really hard to pull off. You don't have to tilt anything, you only need a mass and a force meter. So we also feel that the moment of inertia of the point and the exact energy distribution can also change the exact bouncing of the point. It's still still fits the problem statement. It's not the most relevant. We really like the analytical 3D model. If you use the physics engine, then it should have been definitely analyzed. How does it work? Even more because Unity is mainly a tool for visualization, not much not really usable for exact physical measurements. There should have been other causes of deviation between the 2D and 3D model studied. This is, I think, a really significant point. And also the uncertainty of the theory in the error analysis. So we think there was a good explanation of the phenomenon. The theory was lacking, the exact analytical theory was lacking. The experiments were quite well carried out, however, only some parameters were varied, and the comparison between the theory and experiments was was okay when it was done. So I would like to now invite the opponent to a discussion.
Okay, could I first
Yes, please connect your computer. Please connect your computer.
First, you said I stated that friction isn't as competing negligible. I didn't say that. I just said.
But you said it's not that relevant.
I said the most important parameter is ratio thickness diameter. The second
is the coefficient.
Is the coefficient.
Yes, I can agree with this, but it's still more relevant.
Okay, so the third would be the friction, and I neglected it because I think it's a quite a difference in the importance between coefficient of restitution and friction. But
let's start with this topic if you have brought up this. So I feel like that all these assumptions which you have said to me could be easily verified by simply varying the surfaces at which you have formed lines. So first, maybe the coefficient of restitution, if you think that's that relevant, then you should have done the measurements on multiple surfaces.
Only the coefficient of restitution. Because I, of course, I also thought it would be very interesting to vary the coefficient of restitution to done. But how would you have like?
Well, if the coefficient of restitution dominates the phenomenon, then variance between a really bouncy surface and a not so bouncy surface should have been relevant. But I didn't want to start with this topic. Let me start with another one. But I have my last. You brought up this point by starting. Please let me start the discussion. So the last topic of the quick question was, what do you think is the main deviation between the 2D and the 3D theory are? So you have stated that it's because the gyroscopic effects. Do you believe that? So what do you think if I throw the coin and we define the impact angle like? Can I rubber it? If you have a coin like this, and here it is bouncing, this is from the side view, then the impact angle with this is vertical and this is the impact angle. So what do you think is the probability of the coin landing at a given impact angle in the 3D instance?
I'm not quite sure, like, I can't come up with this, like.
Okay, so I believe that the main deviations between the 2D and the 3D theory are not because of the gyroscopic effect. Of course, they can be relevant, but they are outcomes of extremely complicated kinematic theory. But another extremely relevant point is that when you use a two-dimensional model, your coin, in the general case, has the same probability of landing at any of these impact angles, because it can land by rotating this rectangle around. However, in a three-dimensional case, you have another degree of freedom. You basically can inscribe the point into inscribe the cylinder into a sphere, and you have the same probability of landing at any given point of the sphere. And because of this, there will be impact angles which will have much higher probability of the coin landing on. And this will cause deviation between the two theories. And I believe that this is the main cause by your side probability predictions were wrong.
That the sphere is a much greater area where like
yes.
sides that so you get what I mean. Then why would like it would be the other side, wouldn't it? Like the probability for each angle is the same. Yes, in 3 dimensions, the probability for landing on an angle that is on one of the sides is greater, isn't it?
Yes.
So wouldn't the probability for landing on the side in 3 dimensions, so landing on the side, not, face, I mean face, sorry. Wouldn't the probability when you land on the face greater in 2 dimensions than 3 dimensions? Yeah, sure. What? Does it work?
It is another possible effect, so I think we can now go on.
Okay, yeah, but I'd like to finish this because I'm not sure myself now. How do you think about this? I believe I understand your point, but I think the effect would be the other way around.
Yeah, but the thing is really there, and I think that in your theory and analytical approach would have been quite useful for this.
Okay, so then another thing I would like to point out. He says I didn't use the 2D theory at all. Like
Yes.
I used it the same way I used the 3D theory. In the comparison, I had one graph.
But you have only stated that the main causes of deviation are due to gyroscopic effects, and they were not really measured. So there was no. So, but here the probability of the coin landing on the side is higher than the 3D theory, and that's what you said would happen because of. So we have talked about the same thing. It's not the other way.
I made a mistake about face inside. I think that.
Yeah, but you have really confused me and frightened me, to be honest.
I'm not sure myself. I think I made a mistake.
Okay, so let's move on. I think so. You
to finish this because
we have, I think, discussed it at great success. So what is exactly fitted in this given theory? Nothing fitted. So you have taken out your basement's surface from literature. So
it could be deviation from the basement surface and its reality, but it was not fitted.
okay, so that's definitely.
But like you said, 2D and 3D, 2D was the use, you can see.
It is at use, but if you take so much time with analyzing it, then I think that the deviation should have been much better analyzed because you have only stated what you feel should be the main cause of deviation here. But my next question would be, you have used Unity as your main physics engine, and I have stated that my problem about this is that is that you don't really know the exact inner workings of Unity.
Unity is just for visualizing and not for physical simulation.
It's optimized for different codes.
Okay, how do you explain like?
You stated that the theory works because the Unity's collision response is correct. Then I feel that you should have done comparison between exact rebounces, so exact analysis of the exact collision response of
Like an
Unity.
experiment for the exact.
Yes. Did you do anything like this?
That would be great, but maybe you have an idea how to build a machine that's so.
Well, it's basically the last year's tic-tac problem, so it can be carried out. But I felt like that it could have been incorporated, but it's not the most important phenomenon.
And also I like to emphasize that 3D wasn't like the main theory. You had a lot of physics.
But it is the only theory which fits with the measurements. So it is your only correct theory. You can't say that it's not your main theory.
There are some deviations as well. So what's the main theory?
Okay. My next question would be, your theory is a simulation which uses a few thousand measurements. Did you do any kind of confidence intervals for the theory itself? Because it's of course not a definite value.
No, I didn't do that, but the error bars for 2,000 rows are smaller, and because I simulated it for every data point, so so there are 100 points. If you have that much points and the confidence, so you don't have to necessarily have that great error bars because you have much more points. So that's why I just used some arbitrary. So I fitted it. So I plotted a polynomial of 10 to the 3 through the theory points in order to make it look smooth.
Okay.
But you can see.
I feel like that on your visualization you should have pointed out there are the interpretation points, but you have showed us that before. Yes, you have showed us that before. So about my other. I would like to bring in new topics. the coin becomes much more unstable when you increase coefficient of friction. For example, you have the same impact for the same coin when it sticks down, then it can tip over while
I'm very sorry to interrupt you, but
okay.
You started a topic that you are unfortunately not able to finish. Thank you very much, but you still have 1 minute for some questions.
Okay.
So thank you for the discussion.
Okay, thank you very much.
It's not you.
Let me summarize. So, our main topic of the discussion was the main deviations between the 2D and the 3-dimensional theory. I think I've explained quite thoroughly what I think the main cause of this deviation is and how the reporter couldn't give a convincing answer for this. I think because lots of time was spent on analyzing the 2D theory, one of the first things which should have been explained are the differences between these two. As I have already talked about my lacking of variation of more physical parameters, because the problem statement clearly states that more physical parameters should be varied. However, only one surface was used, and my feeling is that the own contribution in this theory is not that high or should have been expectable for this problem. Thank you very much, and thank you very much for the great discussion. I think
That's it. Thank you. Okay, questions from the reviewer, please.
Okay, thank you. I have a couple of questions. First, a clarification question to the reporter. You say that increasing the angular momentum will increase the probability of it landing on its edge.
Angular momentum.
Yeah, so how fast is spin?
Yeah, but not in all directions. Only in the direction like this.
Yeah, okay.
Yeah.
On page 10, you mentioned all 4 edge points of the dice hit the ground. Could I clarify what you meant by that?
Sorry, what did it?
Page 10, you were talking about all 4 edge points of the dice X the ground.
Yeah, okay. So this sensation works. It calculates for every edge point. It calculates the relevant forces. And normally all forces are relevant. But for the edge points that don't touch the ground, the normal force is relevant.
Okay, thank you.
And because we can still,
Yeah, okay, thank you. So, another question. How high did you drop the dice from?
the same as I stated in the slide about unity, I defined it the same. So I believe 0.25 between 0.25 meters and 0.75.
To the opponent, do you think decreasing the drop height will decrease the randomness of the system?
yes, of course, and also the surface variation, because less bounces decrease the randomization, and also the coefficient of restitution can be different for different
Okay, thank you. I do think 0.25 meters is sufficient.
Well, it depends it depends how did you control for your
Okay, thank you. So next, to the opponent, we were talking about changing the moment of inertia of the cylinder.
Yes.
But I want to clarify, because depending on the axis of rotation, which after collisions will change, what do you think about moment of inertia, because that will be constant?
I meant that you could have used not only solid coins, but for example hollow coins, when the mass is distributed at the outside.
To the reporter, how did you experimentally verify that the mass distribution of your coins was equal?
I didn't experimentally verify, but I choose Beechwood because it is known that it has a very
Okay, thank you. Also, to the reporter, you mentioned that you couldn't really test angular momentum for, so how edge spinning would affect the.
It would be very, very difficult to quantify
To
this.
the opponent, do you think there's a way for him to pretty rigorously control the angular momentum of the dice?
The angle
Experimental setting.
but you can measure the angle.
Yeah.
There is.
Okay, to the opponent, do you think that the fact that his throwing method is very limited, unlike in the
Yes, I think that the throwing method should have been
Yeah,
definitely changed. There is a quite big
all of that.
dance.
Okay, thank you very much. Time for preparation of the review. Okay, time for preparation is up.
Okay, good afternoon everyone. My name is Akshay, and today I will be presenting problem number 7 for the science text. So for the review of the report, the reporter gave a pretty decent overview of the theory. First, he included a 2D simulation and a 2D theory and 3D simulation to test the differences of both of them. Just watch this. He also tested many different geometrical dice, geometrical ratios, initial conditions, and used an improved physics engine to test the result. However, he didn't discuss the randomness experiments. His talking of angular momentum was a little bit unclear, and his discussion of the coefficient of restitution, I didn't understand how directly the coefficient of restitution impacts the 2D or the 3D simulation results. Also, for his experiment, he tested many different geometrical dice. We did not test the coefficient of restitution for the relevant shapes, nor did he talk about any friction measurement. He just said he looked it up online, but it's unclear how you can look up the coefficient of restitution in their own garage or online. Just go My review of the opposition for he mentioned many potential improvements to the report. For example, he mentioned the importance of shape dependence of coefficient of restitution. It's difficult to experimentally verify that the coefficient of restitution for a sphere is going to be the same as the cylinder, although somehow he thinks that it's the same. He also recognized the lack of physical property experiments such as rolling with angular momentum. One way I could suggest to the reporter to test this would be to roll it down an incline. That will obviously also give us a linear velocity, but you can also put it on the treadmill, which would cancel that linear velocity. He also noticed the lack of experiments regarding friction, and friction is important because friction can change linear velocity into angular velocity. However, some cons for the reporter are that the moment of inertia is different for different velocities, so I wasn't sure what he was referring to. His discussion of linear velocity said it didn't matter, even though it can be converted into angular momentum, which contradicts himself. Also, unfortunately, the gentleman kept cutting off the reporter, which was a little bit confusing to hear. Alright, the first key discussion was involving friction. So the opponent said friction is relevant, but the reporter said coefficient of restitution is the most important factor. However, I think that friction is important, as I said before, because it can turn initial velocity into angular momentum. Second one was about inscribing a possible way of improving the theory by inscribing a sphere around the cylinder. And in some impact angle ranges will thus have a high probability of occurring. But the reporter, I wasn't sure what he was talking about, but he mentioned something about the 2D probability on the graph being lower. But I think that the projection from 3-dimensional to 2-dimensional will change the mass distribution on the dice. So I think the opponent will be correct in this case. The third key discussion was about the use of a physics engine. The opponent mentioned that he should test the Unity engine to see how it's correct because he doesn't know the inner workings of it. The reporter mentioned that it's used for visualization. I think the reporter should have a relevant 3D model that isn't taken online, but I don't see how you test it when initial conditions are extremely sensitive. For our first important question was about angular momentum. The reporter clarified that he meant angular momentum referring to the dice rolling on its edge because he mentioned that angular momentum will increase the edge, but if you roll it like this because of conservation, it's going to also land on its head. The second one was increasing randomness. I believe that increasing drop height and increasing coefficient of restitution will also increase the randomness. The opponent agrees that randomness is an important optimization factor in this problem itself and thus should be tested. That concludes my report review. Thank you.
Concluding remarks from the report, please. Okay, guys, let me speak. Okay.
Okay. So thank you for the great discussion. I think many of the points, both here and the comments, are very true. So 3D analytical model would be great. Just to come up with it. Also, I could include my experiments, but a point was brought up that I should vary the coefficient of restitution more. I totally agree. I tried, but it's very hard to find different floors that where the only parameter that differs is the coefficient of restitution. I tried to find it online, and I tried different things, but it's always like a lot of floor probabilities, and it doesn't really stay the same. So that's why I don't have any experiments on the coefficient of restitution. Also to the friction, I believe friction is important, but not as important as the opponent stated, because I didn't conduct experiments, but I believe that the Unity physics engine is very accurate, generally, and it tested different frictions in the physics engine, and they had little to no impact. So that's why I believe that friction isn't that important as the opponent stated. But generally, especially from the reviewer, I believe great points, and also from the opponents, great points. And next time I'll try my best to implement those points, even on a different problem. Thank you for that.
Thank you. Questions from the jury members, please. Okay, Nicola, then Georg.
Okay. So I have a question to the reporter. Can you please connect your presentation again?
Yes, next question. No, I was joking. Okay.
So, okay, can you show us the slide number 10? Yeah, the same slide. Okay. Okay, so, well, here in this formula for the normal force, what is lambda and what is d?
Okay, so d is the distance from the point to the ground, and lambda is the steepness. So how?
Okay, I have a very quick follow-up question. What is the dimension of lambda?
Lambda has no units.
Does the opponent agree about the units for lambda? Okay, so the opponent, the units for lambda?
Why last I didn't have used the force-based
Okay, the reviewer, any idea about the units of lambda? You can say it.
So that should be
okay. Georgi?
The next question. Go to the next slide. Go to the next slide.
11.
The static affection that you mentioned. Static and non-acceleration. I don't think it's me. Yeah, so here, please to comment like what is this static friction, where the debate and so how to visualize it, and also comment on units.
Okay. So the static friction. So in this we don't have a static friction coefficient because the static friction coefficient is like buried in this if statement. We didn't and because we didn't really have a static friction coefficient, we made it like look good, but if it looks good in the simulation and visualization, it should be at least a bit realistic. Now to the static friction force, we looked at the different forces that act on the point, and we said that the acceleration of the point has to be 0 because in static friction the point like sticks to the ground, and like okay.
Quick.
Try. Okay.
I have a question. Please go to 10 again. I hope you can. And let's to the opponent. He says that those parameters f and lambda, they are the same for always. Do you agree that f should always be 2 newtons?
No, of course not. It should be dependent on the time of the impact. On the time of the impact duration. The duration of the impact.
Sorry, I have to clarify that's a mistake because in German the point is like to separate.
So
zeros.
2000.
It's 2000.
Okay. Either way, it should be the same always.
The same point.
The same value.
Is it a universal constant? Like
Yeah.
It's not a
For any dice. For any dice, you will use that too.
It depends on the time
2000.
step.
Okay.
You have to sync it with the time step so that the simulation is the same.
In the Unity engine, what surface conditions did you vary there?
The bounciness of the ground.
The bounciness, so you then vary the coefficient of restitution
Yeah.
in the engine.
Yeah.
Did you pick the data because it looks good, or did you pick the data because that's what you got? Because they match your model and the data matches very nicely. And
So
you
I
mentioned,
actually take the data like, or
in the next slide you mentioned that you picked parameters there that look good. So did you?
you mean this?
no,
No, the previous one.
yeah, here you said like something looks good. So.
Yeah, you said there. No, you picked that value because it looks good.
Okay.
Very quick answer.
We chose this statement that it looked good, but not these numbers. These numbers were that they are numerically stable.
Okay.
Very quick question. Like I missed. So what was your distribution of the like throwing parameters? Like was it completely like random or
Experiment or
both?
experiment, I just threw it in the air, so it should be random. I tried to make it random, and in the simulation, I chose random numbers generated, but it's sorry.
And like if it's something that dies, you really believe the thrower makes it random or okay, sorry. But like you spend the time like that. You have next time like 30 seconds and you're gone. Okay, can you also calm down because Yes, you have to train for the day after tomorrow because they're very quick and professional. They miss the wine. The question is, what can you offer for not being No, it's like you will miss the last. Okay, so ready? So I'll start with Javier, so with the one only, and then continue and end with myself. Grades for the report. Now, 8, 3, 4, 6, 5. No, did you give a 7? That would make full scale. No. Grades for the opponent. No. 8, 4, 5, 5, 7. And grades for the reviewer. Now, 8, 5, 5, 7, 6. Okay, thank you very much. I just quickly borrow the. Your three.
Do you prefer that I do a joint comment on everyone?
No.
No, you must be that.
Okay, just give us the partial grades and quickly.
Okay. Yeah, for the report, I had the main issue for me was that which I think was incorrect. And like the units where I didn't understand what was written there, and also the opponents didn't give you a chance to just explain it more properly, and in the jury questions I wasn't able to understand what was written in the theory. And also it was later to shout the discussion during the opponents and the reviewers. There were many other parameters that you could have read and you could have investigated the problem. So that was a major problem for me too.
Okay, and Javier?
Okay, for me, I think it was really, you explored several ways to get the answer. I like your final, your parameters how to aggregate it. I think mostly it was very good. But I think that if you think the second most important parameter is coefficient of restitution, and you don't change the surface below, it's like the Q is.
So your partial grade?
My partial was 4, 2, minus 0. It's 7, 6, and I don't know.
Okay, so I will give you 4, but I would like also to say some words for what Georgi said. So actually in the task it is written back. You should, what should be the physical, the symmetrical dice, so that it has the same probability to range on its side, on each of its side. So, faces, excuse me. But actually, you didn't answer this question in your presentation, so at least I didn't find the answer. And I agree with Georgi that you had such a long theory, which actually I didn't have the feeling you have used it in your simulations or in your models. Well, my partial grades are as follows. Well, 2.5, 1.5, and -1 due to your obviously wrong answer to my question.
Okay, opponent, also pretty broad set of grades. Georgi, 4.
Yes. So one of the main issues I already mentioned, like you do not use any of your time to just look at the theory and look at the units there to discuss it. Also, you had like your charisma and it was really appreciated. But during the first 5 minutes of discussions, like you were very, very active, and it looked like the continuation of your opposition speech. So that like you were talking what should have been done, what should have been done. You were right in most of the parts, but like I didn't get to the most chance to see what was in the report there again. So yeah, and the most major thing.
Sorry, did you mention your partial grades?
No, 1.25 of clarifying question, which was like, okay, it wasn't good for me. 1.5 in opposition speech, 0.5 in discussion with the reporter, and 0.25.
Okay, so basically, you had your discussion was not appreciated by Georgi. Caveat had a different meaning.
Yes, I like your questions. I think they were really good, and maybe you didn't have enough time. Well, your speech, you seem to have understood what he did and what were maybe some of the weak points. I agree partially with Georgi in that it seemed a bit that you had your speech and there were some points that could have got more fun. But mostly I liked it, and the discussion was actually heated discussion, and I liked it for both. And the grades were 2 for questionnaires, I went to the top. 2.6 and 2.6 for your speech and the discussion.
Okay, and quickly to the review, there was a serious spread between 5 and 8. So Nicola, maybe your 5?
Yeah. So, okay, I gave you 5. Well, to be honest, your review was not bad. You were not able to see your presentation. Yes, so please, next time test your connection to a local before the battle. But still, unfortunately, that was some kind of an average review. So you covered most of the aspects of the report and the opposition. Your discussion, analysis of the discussion was relatively fine. So what I was missing was that you didn't analyze deeply the missed points by the reporter in the opponent. That's it.
Okay, and quickly, Javier.
Yeah, me too. I also like your questionnaires. I wanted also to talk to them for both reviews. I think they were okay. They were not too deep. You have little time and too many issues, so it was not too harsh. But I like that you put out that the linear velocity is important. It can change the question and then change the probabilities, and that was not worked by either of them. So it's important about it.
Thank you very much. Just about very few general comments. One is going towards the report. I ended up being in the middle, but mostly due to different reasons the colleagues mentioned. The first thing is general thing. If you have a theory which doesn't lead to a reasonable result, especially if you have another theory, it doesn't really make sense to spend time on that theory. Theory which doesn't have an outcome, it only makes sense to present it if you have not anything else. The second message is coming from a field where we work with random number generations and random numbers, like DICE is basically a random number generator. So what you try to do, that's the definition of DICE, what you try to do with little randomness, so little good control but not perfect control of how you throw a dice, you get a non-controlled outcome. Yeah, 1 to 6. So basically the starting parameters should be something which is not like completely random, because like it's not a random number generator. Like so the game of a dice is that you try to control it. You are not able to make it perfect, but you try to control it. So you limit the range of parameters to be somewhere, and still the outcome is random. And this is something which none of the three teams like mentioned. So I was not like subtracting points. I just want from a physical point of view. If you are speaking about the dice, that's something you are not able to control if you would like, even if you would like to. That's why we have a coin, we have a dice, like it's something which is easy to control. It's not a good dice. And the third one goes to the opponent. I think like if you calm down a little bit and maybe give him a chance then you might score better. Even though I understood your point, I sympathize with like you wanted, etc. Like all the points were valid and everything, but like then sometimes the appearance is not really good if you are too harsh. So this went a little bit further than I really appreciated. Okay, Taiwan, thanks a lot. It was a wonderful fight. I think everyone enjoyed it with heated discussion and everything. Let's